Swayam Prabha. Digital India. Educated India.
Welcome to Nonlinear Control. So, where we were last time was at the Frobenius theorem. We had started discussing the Frobenius theorem. We are going to continue to actually discuss and talk about the actual theorem itself. In order to talk about the Frobenius theorem, we first introduce the notion of a distribution, which is basically you take all these generating vector fields and you take a span. Yeah. So, basically at every point P in the state space or whatever set you are working with, you get a subspace, right? At every point P you get a subspace. So, that is what is the distribution itself. Okay. Obviously, we do not want the distribution to lose rank or change rank. So, therefore, we talk about non-singular distributions, yeah, which do not alter in rank as you change the point P. So, we will always work with non-singular distributions, and then we stated and proved this lemma, right, which is saying that if delta is a non-singular distribution, then involutivity is exactly identical to the Lie bracket being in delta. Yeah. So, actually I forgot, we also defined involutivity, which is saying that if there are two vector fields in the distribution, yeah, if Fg belong to the distribution, then their Lie bracket also belongs to the distribution, right. Now, we also discussed this that it will lead us, if you want to actually check this in reality, you will have to do all these iterated Lie brackets, so many iterated Lie brackets. So, we came up with a simpler condition, which is this lemma 1.3, which says that if you have k generating vector fields for delta, then involutivity is identical to just verifying that pairwise they belong to delta. Okay, that is it. Pairwise you have to check that Fi Fj belong to delta. Okay. We also proved this. I am not going to go into the proof of this. We also sort of, anyway, did this example on feedback linearization, yeah, this system. And anyway, we just, this is again going back to the previous material. We just took an output which was given to us, right, and then computed the relative degree of the system, right. After computing the relative degree of the system, we saw that it was 2 and the state space was 3 dimensional. So, obviously, I need one more additional coordinate, right, and we saw what we were thinking how to choose it. The simple obvious choice does not work, right, like if I choose z1 is x1, the derivative of x1 contains the control, which we do not like, because in the normal form the control appears only in the linear part and not in the non-linear part, right. So, we do not like this choice. So, obviously, in order to come up with this good choice, we use the definition itself, that is, we want to choose this phi function such that Lg phi is equal to 0, right, and that gives us a bunch of basically gives us just one partial differential equation, yeah, just one partial differential equation which is looking like this, yeah. As you can see, this is not completely specifying the function, but we are just going to guess one possible choice that satisfies this relationship, and we guessed it, yeah. I would say I guessed it, yeah. If you can come up with a more smarter way of doing this, sure. In fact, we can go later and see how to, maybe, I do not know, maybe if it is possible to do better than this, yeah. But as of now, no, we just have this, we are basically guessing this function based on the PD that we have. So, it is not like a completely out in the blue sort of a guess, but it is more like, you have a PD and it is not easy to solve this. So, you will sort of try to do something better, yeah. Yeah, actually you can do something, but I am not going to, that is going to be very complicated, yeah. Guessing is way easier here, yeah. You are just trying to cancel appropriate terms and so on, and we discussed this last time, alright. This I left for you to sort of look at, because this is part of the exercise that was given, but it looks like I have already done something on it. So, I will leave it to you folks to sort of verify this, okay. Now we actually move on to the statement of the Frobenius theorem itself. Why do we care about the Frobenius theorem? Because we are trying to answer that original question. When is it possible to feedback linearize a system, completely feedback linearize a system? Until now we have been looking at relative degree something, right, which is less than n. Of course the Frobenius theorem is useful even then, but it becomes especially useful to figure out when your relative degree can be made n, okay, which means that you essentially have the entire system to look like a linear system, right, after suitable state transformation, okay. So that is the question we are trying to answer. So Frobenius theorem is what lets you answer that question. So that is why we are moving towards the Frobenius theorem, alright. So we make a couple of more, one definition and one theorem, right. So the non-singular distribution delta which is generated by these k vector fields is said to be completely integrable on some open set in the state space if there exist n minus k annihilators, okay. If you remember your vector space course, annihilators are essentially what annihilate the elements of the vector space, vector field or vector space itself, okay. In this case, and remember that the annihilator always has dimension n minus the, the vector space of annihilators is always n minus the dimension of the vector space itself. That is how it works. So in this case you have k vector fields, distribution is non-singular, which means delta is of dimension k at every point p. At every point p, delta is going to have dimension k, right, because it is a non-singular distribution, okay. Therefore we have n minus k functions, okay. So what are these n minus k functions? These are, notice that these are real valued, by the way, these are scalar functions, okay, these are scalar functions. And how do we define them? They have to satisfy that LFIHJ, which is this, del Hj del x Fi is exactly equal to 0, okay. This is actually like an annihilator, okay. So here it is not H itself, but you are taking the, it is not, the H is not the annihilator vector, the annihilator vector is the partial of H or dH, okay, because H is a scalar field or a just real valued function, yeah. But when I take its partial with respect to x, I now get a row vector, right, it's 1 by n dimension, okay. So this is the annihilating vector, okay. So and further you want that these dH is of course this guy itself, we have already defined this notation, dH is this, these dH are supposed to be linearly independent, okay, okay. So if this if these conditions are satisfied, then the vector field or the distribution is said to be completely integrable, okay. This is just a definition, so just keep this in mind, we do not want to go into too much more detail than this, yeah. So distribution generated by k vector fields, I want the existence of n minus k functions such that their dH multiplied by Fi is 0 for all I and all j, yeah, I is ranging from 1 to k, j from 1 to n minus k, okay. And of course these dH have to be linearly independent. As soon as I said this dH has to be linearly independent, you should be reminded of this lemma 0.2, yeah. If you remember, I will scroll back, what was lemma 0.2, yeah, we started saying that some row vectors are linearly independent, okay. So exactly like this, as soon as I say that these dH are linearly independent, you should be reminded of that, yeah. So you are already, it looks like there is a connection between what we are saying here or what we want here and what we were looking for there, okay, alright, great. Then we talk about, in order to actually verify this result the Frobenius theorem, we need the inverse function theorem, but the inverse function theorem is such a inverse function and implicit function theorem. These two theorems are such powerful results that all of you who are doing anything in systems and control, just read and understand this theorem, these two theorems, the implicit function theorem and the inverse function theorem, okay. Implicit function theorem is an byproduct of the inverse function theorem. It is very straightforward. What does the inverse function theorem say? It just says that if you have a continuously differentiable function from an open set in Rn to Rn, and if the total derivative, that is dt of p, is invertible, okay, at some point p. So dt of p is invertible, then the function is not just invertible at p but in a neighborhood of p, okay. So all these results, both the implicit and inverse function theorem results, remember I connected, if you remember when I talked about the diffeomorphism, right, and I said that it's essentially like the equivalent of a similarity transformation for nonlinear systems, right. So when I talked about the diffeomorphism, how did I verify something is a diffeomorphism? I took its Jacobian, and the Jacobian has to be invertible, right. So this is where all that comes from, because if the Jacobian is invertible, that is the dt is invertible at a particular point, then there exists a neighborhood around p in which the entire function is invertible, okay. So is almost like what we do with linearization in controls also we do this, right. We take a nonlinear system and we linearize around some equilibrium point, and then we look at the linearization, the AB matrices, and if they have some nice properties, like if A is a Hurwitz matrix, we say that the system is locally exponentially stable or locally asymptotically stable. So this is almost like that. The derivative of a map or the Jacobian of a map actually gives you something about the invertibility of the map, okay. And this is why these results are rather powerful and applicable in so many different places, yeah. So that's what this is saying. It's just saying that if you have a continuously differentiable function from one open set in Rn to another, and the derivative or the Jacobian is invertible at some point p, you just have to check at one point, then there exists a neighborhood around p in which the entire function is invertible, yeah. Not talking about Jacobian was already invertible, yeah. The function itself is invertible in this entire set, okay. So that's the inverse function theorem, and not only invertible, it's in fact the inverse is also continuously differentiable, okay. So similarly, if you started with a smooth map, then the inverse will also be smooth. This is exactly what we use to define a diffeomorphism, okay. So whenever you have to check that a map is a diffeomorphism, by the way, the map T can be, the dt can be invertible only if it is going from the same dimension to the same dimension, right. So therefore we are always talking about Rn to Rn, same in diffeomorphism, right. It's a state transformation, so the number of states here on the left has to be same as the number of states on the right, right. How do you check it's a diffeomorphism? Just compute the Jacobian of the map, and the Jacobian is invertible, you are good to go, it's a diffeomorphism, okay. And these are admissible transformations, state transformations, like similarity transformations, yeah, okay, excellent, great. Now we are ready to state the Frobenius theorem, okay. Before I state the theorem itself, I will tell you that I am not going to do the proof extensively. The proof is written here, yeah. If we actually end up having time, I might just do a session separately just for the proof, yeah. Proof is quite involved, but I will encourage you to read it anyway. So I'll just give you a short sketch. We don't expect you to do the proof itself, so I'm not going to actually cover it, but later on if there is extra time, I will just do a separate session on just the proof, okay. Alright, it's very, actually this is Vivek's notes, he's done a very good job, because usually it is not easy to find the proof of Frobenius theorem in Euclidean space. Yeah, typically whenever, if you remember, I told you that the reference was Astolfi, Alessandro Astolfi's book. So most of the notes and everything out there, whenever we talk of Frobenius theorem, they are working on manifolds, okay, not Rn. And then there is lot more notation and careful bookkeeping there, yeah. So here everything is proved in Rn, which is rather nice. So the proof is very nice, please go through it, okay, if you get a chance. So let's look at the statement. The statement is actually just two pieces. One, it says that if you, of course you start with a non-singular distribution of dimension k, okay, always, I mean that's what we've been doing. Then in what this entire thing says is two things. One, involutivity and complete integrability are equivalent. Okay, there is two pieces here, although it has long statement here. Involutivity is equivalent to complete integrability. That's the one statement. And the other statement is that, other piece is that if you have involutivity, then there exists some transformation such that your delta looks like a span of unit vectors. Okay, I don't know if you can appreciate it yet. So I started with what? I started with that's what I started with. The delta is what? It's a span of this guy, right? Some k vector fields evaluated at a particular point. What are we saying? We are saying that something rather powerful. We are saying that if delta is involutive in the state space, then it's equivalent to saying that this delta is in fact the span of identity vector fields or the unit vector fields. What is a unit vector field? EI is this, E1 is this. So obviously it's not affected by point P or anything. Everywhere it's the same. So it's pretty powerful. It says that there exists some smooth change of coordinates, okay, such that all these vector fields that you have F1 to Fk looks exactly like E1, E2, E3 and Ek. Okay, alright. I hope you can appreciate the power of the result. Okay, and if you remember, what are these vector fields? They are just right hand sides of differential equation, right? If you, I mean, that's how we have been, if you think about the control vector field, it is something like x dot is ui summation of ui fi. Okay, that's how we've been looking at, right? And it basically gives you what? Directions of movement at every point. At every point a distribution just tells you that what are the directions where you can move using this particular control. Okay, so if I now say that this span f1 to fk, which is some complex nonlinear function, became just span of E1 to Ek. Now E1 to Ek is just, you know what it is the k dimensional Rk. It is a subspace Rk in Rn, right? So it essentially, you immediately can say that at every point in the state space I can move in a k dimensional subspace of that state space. Yeah, and that's pretty powerful. Okay, also if you replace f1 by e1, f2 by e2, f3 by e3, what is the dynamics come out to? Somehow looks like some integrators are happening, right? x1 dot is x2, x2 dot is x3. No? Does it look like it's happening? Maybe not exactly. Okay, that maybe not. That no, it's not. The integrator is not happening very well. Let's not worry about that. But the point is, the key point is, you are reducing this rather complicated non-linear, at every point P you get a different subspace, different shape of the subspace, to a very nice hyperplane. Okay, so this is the power of the Frobenius theorem. One, if you have involutivity of this delta, then you get this very nice hyperplane at every point, yeah, which is the Rk dimensional subspace in Rn. Okay, and two, involutivity and complete integrability are identical, yeah, if you have a non-singular delta, yeah, and that's pretty cool because involutivity was some kind of an algebraic computation, whatever. I mean, you were just doing Lie brackets, yeah, and you just do, it's easy to verify, yeah, and by doing that you actually get that you have complete integrability. And when we actually say it's completely integrable, you actually got these functions h1 to hn minus k. Yeah, that's what it means, right? Complete integrability means I actually get these functions h1 to hn minus k, which the derivatives of which act as annihilators. Okay, all right. So these are what will become our new coordinates, right. So, alright, proof, I will just sketch it for you. Proof goes in 3 steps. In the first step, in step 1, what is being done is just this proof, that if you start with involutivity, any such f1 to fk will become e1 to ek, okay. That is what this step 1 is doing, okay. It does it in a rather nice cool way, okay, but I mean it does not do it, okay, it does not do it in completeness, but it more or less does that, okay, that you are, if you see these f1 to fk's, you started with f1 to fk, these are, and then you ended up with something like e1 to ek, but with something more here, yeah, with something more here, not e1 to ek itself, but up to the kth element this is consistent, right. It is just the unit vectors, first unit vector, second unit vector and so on, but there is some terms here, okay. That is what this does in the first step, yeah. The other thing it also does is, it shows that this new vector fields commute. What are the new vector fields? These guys, okay. And when we say vector fields commute, we mean that the Lie brackets are 0, okay. That is how you define commuting vector fields. It is like in the matrix case also, right, you AB minus BA equal to 0, that is actually the same, exactly this for the matrix case, yeah. If you say linear system case, x dot is Ax, x dot is Bx, this is the Lie bracket, it is easy to compute. If I say f1 is Ax, f2 is Bx, Lie bracket is exactly AB minus BA, okay, not difficult, you can think about it, in fact just a thought experiment. So, Fi Fj commute, okay. So, earlier when you started with f1 to fk it was not evident, but once you do this transformation it is evident that the vector fields commute, okay. Alright, what do we do in the second step? Second step is the complicated step. Actually, sorry, I apologize. Here all you show is that the vector fields commute. That is all. You do not show that it becomes equivalent to e1 to ek. That is done at in the second step. If you look at just the last line of the second step, you can see f1 to fk are mapped to the constant distribution e1 to ek. Okay, and what this second step does is it actually comes up with the transformation, the state transformation. You need a state transformation, right, to go from the f1 to fk vector fields to the e1 to ek vector fields. That is what the second step does. It is rather complicated because it uses flows and things like that. I have actually not introduced this terminology too much. Again, if time permits, we will do a separate session on this, but not right now. Yeah, all I am telling you is what each step is proving. Alright, the final step, okay. Once you know that your f1 to fk's are smoothly mapped to e1 to ek's, okay, you try to come up with the h functions for the e1 to ek system, okay. What did we do? We went from the f1 to fk vector fields to the e1 to ek vector fields, alright. And now in order to prove complete integrability, what do I need? I need to come up with the h1 to hn minus k, that will annihilate this guy, and this is much easier to do, right, because annihilating e1 to ek is much easier, right. What do I say? All I do is I pick this annihilating functions as xj plus k for j starting from 1 to n minus k, okay. I hope this is not getting already too complicated, okay. Just look at this, x1, x2, xk, xk plus 1, I am going to write this as xk plus n minus k. Yeah, you see this vector? Yeah, let's go back to what we were doing in feedback linearization. Let's forget this annihilator business. What were we doing in feedback linearization? Whatever was the relative degree of the system, we were choosing the rest of the coordinates, right? If relative degree was r, we were choosing n minus r coordinates on our own, so that the entire thing becomes a diffeomorphism, right? And in the normal form, of course, LG phi is 0, right? It's almost like that. It's almost exactly like that. Yeah, if you look at this, this almost looks like LG phi, doesn't it? Yeah, because the G, it's the flipped version, the G is this guy, the vector field, and the phi is this guy, right? Exactly looks like, even if I go back here, LFH, yeah, exactly looks like LG phi. This is how I was choosing the new coordinates, right? So that the control doesn't appear. That's all. This looks exactly similar to that. You make something 0, some LG phi to be 0. It's exactly like that. In this case, the G is this vector field and phi is this function. Okay. So that's all we are doing. If you notice, I am choosing the G in a smart way so that this partial multiplied by EI is 0. Now, I ranges from what? 1 to k, right? So, EI has 1 in what position? In the ith position, right? EI has 1 in the ith position and zeros everywhere else. And this I is maximum k, cannot be more than k. Now, if I choose my this guy as j plus k, okay, then where will it have its, if I take a partial with respect to x, this row vector, where will it have 1? Where will it have 1? In the j plus kth position, right? It will have 1 in j plus kth position and 0 everywhere else, right? So definitely so this guy will definitely have 1 in the j plus kth position, this will have 1 in the ith position, and I is less than or equal to k. Therefore, they don't have, this is a dot product, right? So they don't have 1 in the same position, can never have. That's how I chose it, right? This EI will have 1 say here, E2 will have 1 in the second position, okay? This will have 1 in the j plus 2th position, okay? So therefore, they are not going to have 1 in the same position, so the dot product has to be 0, okay? That's it. I am just making the smart choice, okay? Why do I do it in the EI, in the E1, E2, EK frame coordinates? Because it's easier. It's just unit vectors, yeah, much easier to construct this, okay. Now once I have constructed this annihilator in the E coordinates, EI coordinates, I can take it back to the original coordinates, that is the F1 to Fk system, yeah, just by doing a transformation. That transformation comes from here, yeah, that transformation comes from here, which is why this thing is a bit complicated, and it's pretty easy to show that once I make this backward transformation, this will also have the same property, that del Hj del q Fiq will be 0, because I moved back and forth with the same coordinate change, right? I got a very nice coordinate change, okay, and I constructed the annihilator in the new coordinates, then I went back, I took that annihilator back in the original coordinates, that's it, okay. Yeah, the process is simple, notation is complicated, alright. And so what have I done? I started with involutivity, okay, and I proved that I have integrability, complete integrability, okay.